Thank you for being here, listening to me, listening to this topic. This is me. I will not spend much time on introducing myself, but you can see I've worked a long time in the industry. I actually started 3 years before Honeywell, so I worked a very long time for Honeywell, a process automation vendor. Before that, I worked also in cyber-physical systems, automating the packing of typewriters for IBM. We don't have typewriters anymore, but it was kind of a cyber-physical system. I started in '77. That's only 2 years after DCS was invented, distributed control system. So it's a very long time up to here that I've worked with, seen develop from a time where there were no security problems to a time there are, many security problems, let me say it like that. And presently, I am retired, doing education, doing guest lectures at various universities. I'm more kind of a spectator, not anymore a protector or even an attacker. I'm a spectator. And looking at it, I've seen over the years that we became very much focused on the system, on the digital part of process automation. We had a big focus on protecting the automation system, the DCS or the SCADA or whatever type of control system we have. And we were forgetting about the thing we actually secure, the controls, the physical system, the plant. And that's kind of what this picture tries to do, is to get out of this systems, what I call system-centric thinking, that looking at the digital part and forgetting about the process part. And because the process part also offers a lot of opportunities for better defense and offers threats we sometimes not see if we only look at the digital part. So I kind of constructed this awareness model. It kind of represents my own awareness model over all these years. When I was confronted first with cybersecurity problems in the late 90s, when the industry moved from proprietary technology first to Unix type of systems and then to Windows type of systems, and then kind of introduced the security problem with that, with open technology, first only the malware type of threats, but later on also the more advanced type of attacks we have seen. So then you start basically in a very ad hoc mode. There is nothing organized. IEC 62443 was not even started being developed at that time. That's only somewhere in 2003, they started the work groups. Actually, the first official paper was 2012 or something like that, 2011. So it was a long time before people had put things on paper on how to do things. So it was a very, discovery type of world in those types. So that's why I say, what do I need to do? It's all very organized, unorganized. And then later on, we got IEC 60443 and the ISA 99 group that tried to guide us how to secure operational technology. Well, I mention now operational technology. I shouldn't, because that word is only into existence since 2005, 2006. Before that, we just called it process automation or something like that. And then we started to organize things. That's the how situation. And I think that we keep hanging in this how situation. I'll show you that a little later. While we also should look at the what. What are we protecting? I mean, even if I would be in physical protection of people, then I still would need to know a little bit about the person I try to protect. And I cannot just try to keep attackers away from him without understanding what his wishes are, what his movements are, what his behavior is. And we do that at this moment, I have a little bit of feeling. So the what part is the control part, the automations part. And then the last one is you also need to prioritize. And I think, and that's why that's basically the message of my presentation here, I think is we keep hanging in too long in this system-centric thinking and not looking at the control side or what we are protecting. And my world was petrochemical industry, refineries, offshore industry, pipelines, that type of stuff. So not protecting train systems or other locks or marine. That was not my world. My world was petrochemical plants. So the who kind of naturally went into the how situation. So we did our ISA training, ISA certification. I worked personally also at the 3.3 standard in those days. And we created that, and well, it seems to have people following it. People start making security zones, protecting zones, protecting conduits, and having all these security requirements from the ISA, IEC standard. But the next step is the what. And there people seem to be hanging how to make that step, because that step actually needs you to understand what you're protecting. And in my case, that would be you need to understand what is this process that we are protecting? How does a compressor work? How can I damage a compressor? How does a pump work? How can I damage a pump? How does an absorber work? How can I damage that absorber? So for each of these process equipment, there are ways to attack them. There are ways to damage them or to, well, at least disable them. So that what step, that's kind of the gap we need to close. Well, what are the four main areas that you need to shift a little bit? I don't say, by the way, that control-centric thinking, that's the new look at it, is replacing system-centric thinking. No, you need both. Control-centric system is kind of a shell around system-centric. It's not that you can throw away the one part and go only on the second part. No, you need both, but you cannot forget the one, and we are doing that at the moment. And I think when you go control-centric, you have to go from compliance-based, which typically is IEC 62443. That's kind of a set of requirements that you have to follow. And, well, when you have followed them, you can say, okay, I audited myself against that, and I have done that. But are you secure? I don't think so. I think there are still many ways around that. So you have to move it a little bit from compliance-based to risk-based. Why? Because your actual control infrastructure, your plant, differs everywhere. Even if you have a compressor of one company is not the same as a compressor of the other company. There are different types of compressors, there are different dimensions, lots of things make influence. So you have to go to a risk base where you actually study that. The other thing you have to shift is from asset, not looking anymore at your servers, desktops, switches, firewalls, whatever kind of assets you have in your system, but look more at functions. Functions, of course, use assets, but between assets, functions also implement all kind of trust relations. And trust relations cross all kind of boundaries. You can have a beautiful firewall in there, the most expensive one, the best filtering one, but if you have a trust relation in your function, it just crosses it and will do its damage. I'll come on each separately. You have to go from system-centric to control-centric. So that's basically my story. And we're running in sometimes in siloed organizations. What I've seen, I've worked up to 2023 doing all kind of cyber physical risk assessments for very large companies in Middle East, in in Europe, Asia. And then you see very often different organizations responsible for the same. For example, we have process safety in a plant. Is typically responsible for the consequence of what happens in the plant if there is some failure. But you see also that OT security is also trying to claim the same responsibility, only because it's a malicious type of failure instead of a random failure due to wear and tear of the system. So that is another thing. Now let's step back to this risk part, the compliance part, policies, all kind of stuff you're very familiar with, checklists. If we go to the risk-based security focus, then we have to look very much more at the control system, at the installation itself. Yeah, all kind of stuff, and I'll show you that in another slide later, that sometimes process safety is not even looking at, because they consider things as very unlikely to happen. So they don't analyze that part, but from a malicious point of view, very unlikely things can happen. Some sequences of events can happen, either simultaneously or in a specific sequence. So risk-based security, gives you more insight into problems. Another step we have to make, which I mentioned, is to have to move from asset focus to function focus. Well, that's what this slide is trying to show. The function perspective is actually looking at, what am I actually doing? If I have a process control system, there are lots of functions in there. The operator needs to see the graphics of the process, he needs to have the alarms, needs to be capable of making modifications, needs to, lots of stuff to do. Disable all kind of activities. And that brings in all kind of dependencies, it brings in all kind of trust relations that if you do not analyze them, you can misuse them. A very important part I'll talk about later is functional authority. When we talk about typical IT security people, then you authenticate on something, you authorize on something, and you get access. But a process operator also gets access, of course, in his operator station, but only very limited things. He still has a lot of additional authorizations required for him to allow to make certain changes. And so that's what we call functional authorities. I'll have another slide on that. The most important one, I think, where I've seen many big errors made is in this exposure environment. If you look at threat actors basically need three things. They need opportunity, they need knowledge, skills, and they need motivation. Well, motivation is something we cannot really impact very much. We can maybe scare them a little bit by laws, but typically they will not stop by that. Skills, of course, they need to train themselves too. They need to gain more knowledge. But the other one is opportunity. And opportunity we offer through exposure. So when we do not properly secure our system, we create exposure, and that's basically the opportunity for the attacker. So it's two sides of the same coin. And what we are looking traditionally at, and if you look at IEC 62443, then the focus is on attack surface, how many surfaces you can see through the firewall, or see in your server or your desk, your desktop PC. We look a little bit to attack distance when we going to segment the network. We're not putting our controllers in the demilitarized zone of the network very close to the outside. No, we put them all the way down in the system at level 1. and try to protect the path to that. So making life for the attacker difficult. While you look from a system-centric perspective, that's enough. But if you go to a control-centric perspective, you need the third one. You need what we call control proximity. There are functions that can be very close to the attacker that still make changes into the system. If you take, for example, a very well-known example is laboratory information management systems, where they kind of sample the product, and based upon that sample, they might adjust certain parameters in the production process. And that lab system is typically in the corporate environment, in the level 4 environment of the ISA model. And when you make a change there, when you start manipulating those values, and what we have done in recent years is making direct connections between those systems and advanced process control functions, then you immediately basically change things all the way down to your controller because of these stress relations. And there is not really, in many of these systems, a proper check on what is the good value. In the old days, the lab was providing a nice piece of sheet to the operator, and the process operator looks at it and says, hey, this is ridiculous, I'm not going to do it. But nowadays we see more and more structures where the pathway comes from the outside, already determining things in the level of the process. Not only in the lab, you also see that in big data analysis to optimize all kind of stuff. So this is what we sometimes call IT, OT, integration, convergence. That is really causing this parameter to become very important. But control proximity is basically a node that has an immediate consequence for the process, has a very high control proximity. And we are not looking at it. IEC 62443 is not considering that parameter. And it is important. It's important if I put an engineering station in my demilitarized zone so I can start engineering for my corporate network. I don't have to go walk all the way to the plant to do my work. Yeah, then I also move the control proximity all the way to the perimeter and make life more difficult. And so you have to consider that continuously. And that makes kind of this three-dimensional exposure picture, where the system exposure, the traditional exposure, is kind of the shadow of this bigger exposure. Now, what this system-centric view covers? Well, a lot of stuff. It looks at the assets, it looks at the network segmentation, protocol inspection, all the things that, well, if I read stuff on LinkedIn, 80% of the stories goes about that part. What it misses is this control proximity. What I mentioned is functional authority, all these different levels in a process control system, what you are allowed to do. And there are a lot of settings in there, a lot of limitations that you can build there. You miss the operational context in it. You miss the function to consequence mapping. And the zones are basically created on security characteristics. So nodes with the same security characteristics you put in the same security zone. But that doesn't really mean, in all cases, that these nodes have the same impact on the process. And sometimes you see very important nodes coming in very high levels of the system. For example, a well-known example is field device management, which is managing your actuators, your valves, your transmitters. Well, it is very regular that you put that type of function in level 3. Because they say, yeah, it's kind of maintenance function, so let's put it in level 3. But it has a direct ability to close a valve, to change your operating window of your process. It can even reverse control. And some sensors allow you to put the low limit above the high limit. And the moment you do that in a sensor, you basically reverse process control in your whole control action. So that type of stuff is missed by that. Well, what we actually need is this kind of total environment where we have the system-centric part and where we have the control system-centric part. They are not living apart from each other. They need to be both there. So sometimes it might look like I'm criticizing a little bit IEC 62443 or so. No, they're focusing on system-centric security. And that's in their target, that they are not organization. ISA 99 work group makes its specification for a lot of different industries. Like the 61511 is only focusing on process industry. And the ISA 99 is not doing that. And so the ISA 84 is very specific for the process industry, and they should cover this control-centric part, which they partially do, but in a lot part not. And ISA 99 is doing a fair job on the system-centric part, but yeah, we're leaving out a big gap. Then this organizational ownership, I already mentioned it. We often see nowadays OT security organizations, in the bigger plants at least. Smaller plants still wrestle, and they generally don't have the resources, so they hire people outside and to do things. But in the larger companies, we have often specialist groups dedicated to OT security, and we have groups dedicated to process safety. We already have those long time. Process safety kind of developed in the early 60s still, what it is now. And my view on this is that they both seem to own the consequence, and we should only have one owner of consequence. We should only have one owner of cyber-physical risk. And in my view, that should be process safety. The other people say it might be operations, but operations is not typically an engineering environment. And process safety, that are still engineers. So that doesn't mean that one replaces the other, but they need to very tightly cooperate, and there need to be a single ownership of the consequence. And that consequence, that's very important. In our industry, in the process industry, that can be fatality, there can be death, or environmental damage. It's not a small thing, and you should have only one owner for that, one set of risk criteria to meet it. So, if I look at it in a little bit more detail, you start with the process hazard, which is the consequence. Maybe something explodes, maybe loss of containment, maybe some other stuff that happens. That happens because of a specific function. By loss of containment, maybe something wrong with my level. I have all kind of functions controlling that. Interlocks, emergency shutdowns, operator response, alarm logic. And it is typically caused by either wear or degradation, fully covered by process safety. They analyze in their HACCPs, in their process HACCPs, what happens if my valve fails closed. And then I start thinking, okay, this can happen, and how can I safeguard that situation? Human error is also typically still included in safety HACCPs. Misconfiguration, already a little bit on a tricky part. Sometimes it's covered, sometimes it's not covered. But malicious interference is never covered. Process safety in their HACCP analysis, they do not cover that. I've been in tens of HACCP analysis by building all kind of new plants in the Middle East, in Asia, in Europe. This is not covered. There's 3 months of discussion on what can go wrong, but malicious intent is not a part of that discussion. But it's the same consequence, different causes. So in my view, it should be the same ownership. So this is what I think should happen. When we go from OT security, is not giving this control view, and we should kind of shift this ownership from having two separate worlds. Let me see if I can have have here a light. I was looking for the red light, but it's a green light. So that's a kind of shift, and the other shift is, we have to start, or we better stop ignoring the process. We should stop ignoring the thing we are safeguarding, securing. And that's what I think is happening at the moment. Too much, at least. Now I get to the last 18 minutes, cyber-physical risk. People that follow my publications shouldn't be worried, because I can go very deep in there, very endless discussions on risk aggregation and the difficulties of that. I skip all that. I just touch on some highlights. But it's important that with cyber-physical risk, that we can start quantifying the seriousness of specific hazards and threats. And I say specifically quantifying because in the world I have been raised in, the refineries, the petrochemical industry, all security criteria or risk criteria are quantitative. When I built a plant, I built a plant new in Europe, then my safeguarding should be such that there's never more than once in a million year a fatality. In the older systems were once every 100,000 years. When I started working, there were even countries where it was once in the 10,000 years. So there are all kinds of changes in that world too. But now in the European Union, it is for the old sites is once every 100,000 years, for the new sites once every million years. But that's quantitative. And it's rather complex to express that also for malicious intent. This is an example of a very old issue, but I picked it because it's so typical that you can almost immediately see a threat actor can also do this. Because what happened here was a thunderstorm, and the thunderstorm kind of caused the valve to close. That can happen. I've seen very heavy thunderstorms in open areas where plants are, and those things can happen. But at the same time, it was closed, but the operating system, the DCS system, showed open. So operators really didn't know about that it was closed. And operators started pumping, in this case, hydrocarbons into a dead-end vessel, building up pressure. And there was also overpressurized, then went into the flare system. There you have kind of a knockout drum, and a knockout drum is the basic piece of equipment that tries to separate gas and liquids. It's a very simple device, just kind of a vertical wall in there, and the liquids stay below that, and the gas go over it. And you need that, because if you go into the flare with liquids, you create something you call burning rain. And instead of having a nice flame, you get it looks very beautiful, by the way, but it's very dangerous because it's hot fluid going down. People walking there might be injured. And in this case, it was also combined with a rupture of piping. So it actually released a big vapor which ignited and injured only 26 people. I say only 26 people because this type of incident can also kill people. We have seen incidents where tens of people were killed. So this whole scenario is simple to repeat in a cyber attack. Well, simple, you have to do certain things, I'll come to that later. Well, what is a cyber physical system? Basically, two parts. We have the physical part, which has all kind of limitations. If I have a tank, that tank has a specific volume, and that's fixed. I mean, can only put in so much liquid in that tank, and it has a certain maximum pressure, and maybe there are maximum temperatures. And all of that, those whole physical installation is kind of having a logical mirror in the operating, in the control system, in the automation system. So if I have a tank, well, I have somewhere in my DCS system or a SCADA system, I have some level, and I have a level range that limits that. But that's kind of a logic thing. It's not a physical thing. If I change that, if I double it, then my tank will be 2 times as big. But the physical thing is still the same size. Yeah, so we have a problem there. We do that. So we have this logical mirror. We have kind of sequence of activities, not only in batch, but even in continuous processes. The process goes from step A, B, C, in a certain sequence and certain control activities. So you have this image, and this image is kind of depending on if things work yes or no good. If I start messing around with it, I get all kind of problems. Well, this is something you can, if you look at a digital system, we often talk about vulnerabilities. I prefer to use the word attack enablers, because that's a little bit wider than vulnerability. But also a cyber physical system has attack enablers. For example, the safety margin. Of course, it's such that you do not operate your system to the limit. You always keep a certain margin there. But over time, you've seen these margins decline because processes need to be more productive, more efficient, very often operate even above their design capacity in certain cases. So you have the safety margin that determines a little bit how critical particular disturbances are. You have your physical limits and the logical limits you can actually change. You have the change control. And change control is, by the way, not only happening by making changes in your configuration. I've also seen that change control happens by replacing equipment. I have seen cases where counterfeit sensors were implemented in the system because they were very nice priced compared to the original type, but the actual spec was not the same. And in this case, it was in an ATAC SORN, an explosion-proof SORN. You need very specific sensors that have specific testing. So change control is also a very important mechanism you can misuse to put your attack. Yeah, your response mechanisms, let me see, physical state, reality. Well, I think the other ones are kind of logic, putting the wrong button. This top one is kind of my story on this double ownership. So you can also look at cyber physical systems, at particular ways to attack. And actually, if you, well, I worked since 2014. I think I did my first cyber physical risk assessment in Dubai. Till my retirement in 2023, we kind of constructed also a library of how do you attack an absorber, how do you attack a distillation column of a specific type, how do you attack a pump, and all that type of stuff You can help you with your analysis. You can cross-check with what the HACCP has identified. You can add to that. Well, this is what process hazards are looking at. On the left sides, it's looking very often to single-point hazards. So a valve that fails close, or a pump that fails, or something that starts leaking, all that type of stuff. It's based upon random independent failures. It mainly looks at mean time between failures and determines on that a little bit on how often, how frequent these errors happen. Single deviations relies on the likelihood data that discount rare combinations. So if I look at the right side, the orchestrated attacks from a cyber-physical attack scenario, well, you have multiple failures that can occur in parallel or in a specific sequence. Process safety doesn't analyze that. They consider that so unlikely that they do not focus on that. Even today, when I did my last assessment in 2023, in the process safety analysis, none of these scenarios were covered. And there are in all plants, there are lots of these scenarios. If you look at the process HACCP of a company, then typically 40% of the identified hazards can be recreated by cyber means. That is typically the 60% of the hazards they identify are mechanical type of stuff that can happen, but there is a category of about 40% that is really, you, as a cyber attacker, you could do it. It requires a lot of knowledge, but you can do it in typical things. And from that area, there is also a group of hazards they do not look at. And some of these consequences can even be bigger than the consequences they have looked at, because if a particular combination happens, that can even escalate the impact. So they're not looking at that. They don't consider that logic is manipulated. That's a kind of an important difference. So logic is not failed. So it can be good at one time, bad in the other time, good at some other time. That is kind of the things that do not happen that much in the process safety side. Alarms, safeguards are intentionally bypassed. Timing is precisely exploited. Timing is typically also of importance, not only in batch processes, but also in continuous processes, can be a very important factor. So if I look, going to speed up a little bit. If I look at what the cyber-physical system is for me, well, the right side, the yellow part, is the process automation system, it's the digital part. The left side, the physical system, that's the pipes, the columns, and there is something in between, which I call the interface part. And that's partly part of the physical system. If I have an actuator, I actually built that into a pipe. I have pumps that I can directly connect to the digital system. I have process analyzers and all kind of stuff that's kind of in this in this integrated portion. And when I talk about cyber-physical risk scope, it is, let me go back for one moment. It's all of this. So, and what I see in many analysis, that people often talk about cyber-physical risk, but actually they mean OT security risk because they focus very much in their analysis on the digital part. They do not include this physical part in their analysis. So for me, the cyber-physical risk is everything, and when I talk about OT security risk, is basically my digital risk. So what happens? My attackers attack the digital part, and the digital part is basically responsible for the likelihood. If a risk is a combination of likelihood times impact, and my likelihood is determined very much how well I protect my infrastructure, my nodes, my system side. My impact is very much the process installation, but that's also designed. I have my P&ID, I've made my process flow diagrams, my control narratives, all kind of stuff describing that. But I can make certain choices here that makes life here more difficult. I can keep things separated. For example, instrumentation error is something which I often see, instrument error, often see built in my DCS system, while I'm never switching that on and off every day. So it should not be a problem for me if I need to switch it off or on, to walk toward it and yes or no, switch it on. When the moment I put it into my DCS environment, then it immediately becomes vulnerable for attack. So this is the most difficult slide. I left it in my original version. I had a long story on cyber-physical risk, but I removed all of that to make life a little bit easier. But if you want to estimate quantitative likelihood value for risk, what you basically do is a bottom-up perspective. You look at the components first, you look at the risk, each of the components, by kind of attacking them through a model with all types of cyber attacks you can think of. How do I attack this controller? And you look at what kind of failures or what kind of protections have been created and what kind of functional deviations can be caused. Based upon that, you have all these individual values that we call probability PFA, if attacked, probability of failure if attacked. I lost the word. PFA, probability of failure. Oh, it's here. And each node has a PFA. It has a PFA per threat actor, because different threat actors, different skills, different opportunities. So that makes a change. And then in the end, you kind of have all of those individual values, then you aggregate them along an attack path, and they have a certain hazard connected to an attack path. And if I still have 132, but I do not have more than this one slide kind of summary. Integrating cyber and process risk, shift from system to function focus, that I think we should try to do. Build control-centric risk models, embed security in process thinking, because it works two ways. The process safety people also have to start thinking a little bit more devious and malicious. It's not only the OT security people that have to think that way. It's kind of it's not one or the other. It was kind of a pendulum, moving each other. Extend monitoring to control misuse scenarios and assign functional authority things. Now, I have 40 seconds. I leave that to you. Thank you.